Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Taqiyya Najla Syarif with student number 2206829950. Today I'm going to presenting my final exam answer for numerical method class. Let's move on to the first question. This is the question, and then we're going to solve this question with a framework called the E5. Okay, the first is intention. The aim is to model the suspension system of a satellite transportation trailer (STT) using the three different shock absorber. We need to determine the critically damped value for each shock, compare it to the given damping coefficient, and solve the spring mass system for both the given and critically damped values. Finally, we will analyze the result to decide which shock is best for the STT suspension system. And then next, this is the initial thinking. To approach this problem, we have three critically damped value calculations, spring mass system solution, and then compression and analysis. For critically damped value calculation, which means we need to determine the critically damped value for each shock absorber using the formula for critical damping coefficient beta critical. And then on the spring mass system solution, which means we need to solve the differential equation for a damped harmonic oscillator for both the given and critically damped damping coefficient. And then the last is compression and analysis, which means we will compare the response of the system using each shock absorber with its actually damping coefficient and its critically damped value. The compression will help us decide which shock absorber provides the best performance for the STD suspension system. Okay, next, this is the idealization. We have model assumption and then equation of motion. In model assumption, the trailer is loaded with a satellite mass 1,800 kilograms, and then the displacement of the shocks before loading is 3 centimeters, and the system is assumed to be at equilibrium when the satellite is loaded. And then for the equation of motion, for a damped harmonic oscillator, the equation of motion is given by that, and then the critically damped condition is achieved when that. Okay, we will solve this differential equation for both the given damping coefficient beta and the critically damped damping coefficient beta critical. Okay, move on to the instruction set. We have four, I guess, yeah. No, we have three. The first is determine the critically damped value for each shock. Okay, first thing first is calculate the beta critical for each shock using the formula, and then compare the given damping coefficient beta to beta critical. And then, okay, for the each shock, there's air coaster, cloud riders, and then extreme shocks. We have the beta critical, and then we calculate these values using Python. This is the Python that I made, and then we can execute the calculations. So we have the result. It's like on the presentation. Okay, step 2 is solve the spring mass system. We will solve the differential equation for each shock using both the given and critically damped damping coefficient. Okay, it's like there's three air coaster, cloud riders, and extreme shock. In air coaster, we have the damping coefficient beta and then the critically damped. So as cloud riders and extreme shock. And then we need to solve the differential equation, and we use the Python SciPy library. This is the Python that I made. This Python will provide us with the plots showing the displacement over time for each shock absorber with both the given and critically damped damping coefficient. Okay, next is analyze and decide. From the plots, we will analyze the performance of each shock absorber. For air coaster, is check if the given damping under damped result in oscillation and how quickly the critically damped system stabilize. And then for the cloud riders, compare the damping with the critically damped response. And from the extreme shock, evaluate how close the given damping is to the critically damped value and its effect on the response. Finally, we will decide which shock absorber is best based on minimizing oscillation and ensuring quick stabilization and cost effectiveness.